Hello, everybody, and welcome to Live from the Lab. So today's topic is decoding XRD data using DIFFRAC.EVA. So XRD data, when we look at it, it's just kind of this wiggly line oftentimes. Sometimes it might come in the format of a picture that we then reduce to this wiggly line. But we need to sometimes, pull depth. We want to pull information from that. What do these peaks mean? Why do we have this axis on the bottom? And how can we glean that bit of information out of it? So that's the topic for today, and that is all done in a program called DIFFRAC.EVA. So in order to see this, we're going to actually look at it live in action. With that, we're going to head on over to the table and talk with one of my colleagues. Hello, Nate.
Hey, John.
Thanks for joining us. So this wiggly line. Now, this ends up having, we do have a lot of video content, so if anybody wonders, what is XRD? There you go, you can get it. But just kind of the real quick, you have these peaks and they're at certain places. What does that mean?
Yeah, I mean, like, what makes this different from any other analytical technique with another random wiggly line? Right. Yeah. Why are you the way that you are?
That's right. That's right. So what are the positions?
Yeah, so what we see is, of course, like any day that we're going to be looking at. We've got an x-axis, we have a y-axis. Y-axis is going to be intensity. So those are the number of x-rays that are hitting your detector. So that's easy enough. Along the x-axis, though, generally speaking, you're going to see something called 2 theta. So if you check out our YouTube list for what is XRD, what you'll see is like, you've got a tube and a detector, and they're both moving at an angle, generally, and so you've got
theta and theta.
Theta and theta.
2 thetas.
So 2 theta is what you see along the bottom axis. And this, if we go back to Bragg's law, what this is this is going to be specific locations and specific distances within a material. So remember, this is what we're looking at when it comes to a crystal materials. We're looking at characteristic spacings within a crystal material, the distances between atoms this way, the distances between atoms that way, planes of atoms or planes of molecules. I remember a couple of episodes ago, we had like the Lego blocks. I'm like, it's the length of the Lego block. It's the height of the Lego block. That's what we're looking at.
Nate, that was like 18 episodes ago, because today's episode actually is our 20th episode, so that's actually really exciting. Okay, so we end up having then these like kind of characteristic spacings, and those correspond to the position of the peaks. Now the peaks often have like different heights too, I've noticed. Now, what is that kind of relative to?
So the height can come from a couple of different things. On one hand, the height can come from things like symmetry or multiplicity or having specific atoms at specific locations. Has to do with the size of the electron cloud. But the other thing that people are often interested in is quantification. So like most analytical techniques, more intensity means more stuff. So if you have a lot more of a material in your sample, then you would expect to see more intensity. I mean, we can see this as simple as like if you have a sample holder and you put just a little bit of material in there, then you don't get quite as much intensity. But if you really pack it with material, then your intensity will go way, way up.
And just to make that 100% clear to everybody out there, in XRD, it's not one peak is one phase. It's one set of peaks. I think you like to say it's kind of like a fingerprint.
It's like a fingerprint,
Yeah, so you have many different ridges.
So you're actually going to be counting like the number of fingerprints, not like the number of lines on your fingerprint.
And what matters is not just kind of the position, it also matters is the height of the peaks within that pattern.
Well, and one of the things that I've always tried to encourage people whenever I'm doing trainings or when I'm teaching, is make sure that you're looking at the right, set up your experiment right. Like all good science is making sure that you've done your due diligence before when you're setting up your experiment. What are you looking for? Are you more concerned with are you more concerned with peak locations? Maybe the phase ID part of it is more important. Are you more concerned with quantification? Okay, well then maybe you need to take your data and move it a little bit forward. And that's what I really like about EVA is that it's sort of like our central workhorse for data analysis. And you may take that data and then move it over into, say, a stress module. Or you may take it and move it over into, say, Topaz, which is our refelt software. But EVA is designed to sort of give you all of the capabilities in terms of like the graphics formatting, in terms of the data display. One of the things I'd like to show a little bit later is looking at not just one pattern, but looking at multiple patterns. Because sometimes qualitatively, you can glean a lot of information not just by looking at one wiggly pattern, but by saying, if we come back to the fingerprint analysis, oh, well, those are 2 different fingerprints.
That's right,
either two fingers or 2 people.
That's right. So So you had mentioned, so EVA does the data display, and we can look at 1D data, we can look at the 2D, actually coming off 2D detector, or we can make 2D images out of 1D data, kind of multiple sets. We can do this phase identification, which is like the fingerprinting. We can do something as kind of quantitative. Sometimes we call that semi-quant, right? So we get a rough idea how much is there.
Scaling intensities, And
then kind of pushing the boundaries these days is to say, well, what if, though, this is something different or something new? It's not in a database, right?
So like for most fun science, right? It's like, what if you don't actually have all the pieces of the puzzle? Okay.
Right. So now we can also, one of the most innovative parts, I think, of EVA is the ability to do some quantitation if you don't have it. We call it Squall. And then you can also look at data on its fundamental level and just say, hey, you know what? This scan, that looks a lot like this scan. And then this scan, it doesn't look like that one so much. And they call this cluster analysis, right? You could take in hundreds and hundreds of patterns, compare them, and see that similarity. So EVA covers a lot of things, but enough talking about it. I think we are ready to see it in action,
so let me grab my laptop real quick.
So. All right, well, okay, Nate, so you're going to fire up a video of this, right? So it all goes smooth. No, we are doing live on the air. So we're going to put not only the program to the test, but we're putting Nate to the test.
And we're putting, my version of Windows, which I haven't updated in a couple of weeks, to the test. So hopefully we don't have any.
Let's see if IT shuts us down.
Right. Okay, so if we look at my computer screen, what we've got right now is just a piece of data. So this is one of our tutorial training sets. So this is boiling chips. So if you remember back to Jin Kim, these are the little rocks that you would throw in a beaker to keep it from boiling over. Or if you make pasta right, and it always boils over.
And just kind of as a general orientation point for people who might be new to this, on the left side we see kind of this explorer that gives us the different items.
So everything in EVA is going to be panel-based, right? And so the two panels that I generally like to operate with on the left-hand side is, it's called the data tree. So this is where you're going to hold your different raw files. If you do an identification, a pattern will go there. If you insert a bunch of peaks or you do like area calculations, all of that will then flow down from here. So it's kind of like a lot of graphics manipulation software where you have sort of like this parent-child relationship.
Yeah, we kind of saw a similar layout actually in DIFFRAC texture, and then we saw that in XRR the other day.
Oh yeah, I forgot about that one.
So we got that there, and then in the middle we've got the plot.
The actual data itself. And then on the right-hand side is going to be our properties. So this is contextual. So whatever I have selected in my data tree, I will then have options over here in the data properties panel. So
great.
We're going to start out by doing phase ID.
Phase ID.
Phase identification. So I've got this unknown. Right. I mean, I know what it is, but maybe, maybe those in the audience don't. So we're going to start out by right-clicking on a raw file and going to Tool. And you'll see all the different options in terms of different utilities within our software. So we're going to start out with search match scan. And search match is going to
done.
So search match is going to give you different options in terms of your database options. So we've got a couple of different databases available for us today. We have the PDF database. So this is a managed database from a nonprofit called the ICDD, so the International Center for Diffraction Data. So this is the powder diffraction.
Shout out to the ICDD people.
Hey guys.
So
the PDF database comes in a couple of different flavors, but it is the PDF is for the powder diffraction file.
Right? And so that's a great database in terms of it's actually edited. So those people at the ICDD, they work very diligently to go through the patterns, make sure that check them all out. They're complete.
And so they've had all this data in here. What we're going to look for is basically these sticks. So the peak locations, the relative peak intensities, and these are called cards. And one of the cards. Right. So
I mean, I'm aware that back in the day, there was like a book. Right? So what we used to do, I know at the university, I would go like, I would really be kind of torturesome to students. I shouldn't say that, but so we'd be like, first you got to start with the sample. Now you got to grind it for like 2 hours. Right? You got to grind it, make it perfect, and then you got to run it. And then after you run it, now you got to find the tallest peak, and then you look it up in the book.
It's like indexing by hand, right?
Yeah. But the cards you said, now I know the book. What's the cards about?
It was actually a card catalog.
Really? Like a library?
Yeah. Did you have a library card?
Of course,
I had a library card.
I have a library card.
You still have it?
Of course. But like,
do you remember actually having to go through the card catalog?
Yeah, I do. When I was little,
Dewey
there was the
Decimal
big
System.
thing, and you had to go through the cards.
Yeah.
So that's really how it used to come.
Like when I started in college, like when we had to go up to the stacks, library stacks, and like actually pull books and pull journal articles that were bound, and then you had to like go and like photocopy them.
But they had
a card catalog
for the PDF.
Yes. So you didn't go onto a computer and like look it up. You actually went to this card.
And when
catalog.
you bought it, they would have to ship that to you.
Exactly.
Wow.
So you would like look through it, and there were physical cards. They were like index cards, or like a card that you would have like a recipe on or something. And so these cards would have the biggest peak, the next biggest peak, and the next biggest. Usually it was 3 peaks.
Okay.
And so from this, we would look and we would say, all right, biggest peak number 1 is at 26 degrees. The next biggest peak is at 30. The next biggest one is at 15. So with these 3 peaks, I've got a partial fingerprint, right?
Yeah.
And now I know what I think this material is.
And I remember if you had the really fancy book, it was like twice as thick because every pattern was listed twice. It was the first intense peak was the first one, and then the second most intense, they'd list that one first.
It was like a flow chart, right? Yeah. So you would filter out by the biggest one, and then from the biggest one, you would go down and see like, all right, so what's your next one? And you would just sort of filter through it. And so that would work out nicely if everything were cubic or tetragonal and you didn't have a lot of peaks. But you start getting to some of the grosser looking like monoclinic or triclinic where you've got 30, 40 peaks to deal with, and suddenly that becomes a lot longer process.
Yes.
So, I mean,
and nowadays we're up to like hundreds of thousands of these patterns.
Hundreds of thousands, right.
So
going back
luckily,
to the computer, though,
now we're in the computer. And the other thing I noticed, though, is that there's one called an open database.
So the crystallography open database is another option for searching through the database. So it's another searchable database. I like to think about it kind of like Wikipedia, but for crystallography nerds like me. Right. And so the crystallography open database is sort of a community managed database. There's an online repository at it's online, so it's crystallography. So if you Google crystallography open database, you'll get right to it. And so what Bruker will do is, about once a year or once every, so many months, we'll go through and we will compile this as a readable format. So it's the names, the compositions, the crystal family, the unit cell parameters, the peak locations, the peak intensities, and we'll compile it into a searchable format for EVA. And so it is one of the nice things is that for training purposes particularly, right? You've got a lot of you've got 30 graduate students or undergraduates or whatever, and you want to teach them all how to use this software because there's so much of diffraction that is not just use the right instrument. It's not just prep the sample right. It's also how do you convey your data in a meaningful manner. And so then you can provide this open database to all this, to every student who has an instance of EVA open. So I found it's been a really, really useful thing to have.
So COD, open database, just realize it is not edited. Sometimes when you get structures out, they're in a little bit of a wonky format. You got to fix that. PDF, on the other hand, edited, very trustworthy. So that's how those pull out. Now, if you also, though, maybe you look at always the same materials, right? If you look at cement, if you look at things, then you can create this thing called a match list, right?
So right next to this for the database, what we see is a match list. I don't think I have any. Oh, yeah, actually, I had made one. I made a smaller subset called carbonate minerals. So there's a couple of things you can do with match list. So if we look at the database itself, the database for the 2022 PDF release is, let's see, really tiny font, 460,954 entries, right?
A lot of candidates.
A lot of candidates, right? So there's a lot of data in there. And one of the things that, if we come back to that whole fingerprint analogy, one of the things that I like to do is I like to think about it in terms of having a very curated list, right?
So, fingerprints on the glass. Well, you know what? We can say who was at the party to start with, right? Or who was probably.
Or if you know that fingerprint was taken in, the northern hemisphere, you can throw out everyone who has never left New Zealand. Right. So that's one thing of doing.
So in the analog would be if we're doing a search match and you're looking at cement, it's generally going to be certain things.
Well, I mean, and looking at this, so like even something as simple as like organic or inorganic. So as one of the resident chemists here, right? I like this. Like, does it have carbon in it, or is it or is it inorganic? But then in terms of user-defined match lists, you can use this in a couple of different ways. So you can either, so say you're making, engineered materials or custom blends or something like that, and you want to build up a user library of stuff that isn't in any of the databases.
Okay. Yep.
You can make a searchable database that is customized to your science, your projects, your materials, your formulations, your whatever, and that can be a separate user database. So that's one way of looking at it.
Yeah, like I used to work at a foundry, and what we did is there was Monday, there was the Monday pour, and the Monday pour had a certain chemistry to it. And then there was the Tuesday pour and the Wednesday pour. And of course, by the time you get to Friday, you have the dirtiest pour because over the weekend, we'd refurbish the furnaces. Yeah. So what we would do is I didn't care. I really didn't care what the individual things were. All I cared was, are we doing Monday on Monday, or do we all of a sudden have Tuesday on Monday?
Yeah.
So we would use a database like this, and I literally went in there, measured pristine samples of each, and I said, Monday.
This is a Monday.
Tuesday, Wednesday.
This feels like a Monday.
Very easy, right? Because and in metals, in a foundry, this really influences grain size, ductility, things like that. So, knowing it's Monday is on Monday, first thing in the morning, that's a great thing. And that's actually where we would use user databases. Yeah. So it's a really, really a great tool.
Well, I find it's also very useful in terms of things like, exploratory or, I guess I said earlier, like customized things.
Yeah,
right?
New materials, things like that. Yeah. So, but now match lists, those are a little different,
Match list is a little bit
right?
different. So a match list, I like to think about it as a subset.
Subset.
A subset, right. So the match list are going to be, so like one of the ones that I have here is a selection of carbonate minerals. So on a project I was working on, we were looking primarily at carbonates.
Yes.
So I went through one of the databases, I can't remember if it was a PDF or COD, and pulled out all of the different carbonate minerals, so calcite, dolomite, anchorite, siderite, all the different ones that I wanted to use for. And so then it was a much neater subset of things. So I guess you could kind of think about it like, so one of the things I love about Madison is Restaurant Week, right?
Yep,
and so you don't get to pick from the whole menu, right?
Nope,
they have a curated list of
go.
things, and it's like, of these like 4 things, which ones do you want to pick?
Yeah.
Right? And so it streamlines things for the kitchen. And same way here is like, if you have a match list, you can set it up so that there are very specific, say like cement. You gave a really good example with cement. You say, give me all of the associated minerals for cement, for clinker, for raw rocks, and whatever. And then you don't have to worry about like a random uranium ore showing up, or like an organic, or like a polymer. Or
so
it's
a great way to build in the intelligence. You might have a specialist come to your site, set up a match list, and then you know what you're going to be looking on as a great subset of that larger data.
Bespoke solutions for your analysis.
Okay, so now we got a database.
So we've got a database.
And we're going to do our search.
I've apparently already searched this, right? Yeah. But so what we're looking for is peak positions and intensities. So I'm generally going to bias a little bit more towards peak locations than peak intensities because of things like texturing and peripheral orientation.
Okay.
Sounds like a great topic for another Live from the Lab in the future, but for now, just know that we're going to be
So the relative intensities are based on the fact that you think it's a completely randomized perfect powder.
Well-prepared powder, right. And so what we see right off the bat here is, so I've got my collected data in black, so this wiggly line here. The stick pattern here in red is going to be for the first proposed match. Right, so this is going to rank based on this figure of merit and a match percent. So this has to do with how many peaks have been matched, how close they are to the observed maximum. And you'll notice I didn't do any sort of peak searching, right?
It just popped up.
It literally just popped up, right? And that's one of the nice things about modern search match algorithms is that they will handle just the raw data. It goes through and it says, I think this is a peak because the Y is changing very quickly. Right?
Okay, so you don't have to go in and manually say the peaks are here, here, here.
I literally just said search match versus the scan. Which is super, super convenient.
And now we got this result window kind of on the bottom. And I see the top one, it has this really high percent number. I'm guessing that's going to be a good match.
Yep, so this one's going to be a good match. And so I like to sort of visually confirm it. You have these sort of like dotted lines on the bottom. You have your sticks to, and so I look at it and I go, you know what, this is my biggest peak, right? I've got a couple of smaller peaks. They've got about the right relative intensities. Great, this looks awesome. If I click on this, what's going to happen is I'm going to actually add it to this list here, my pattern list over on the left.
Okay.
So you see that now it's tied to the raw file.
Yeah.
So if I'm working with multiple raw files, I can have individual identifications for each piece of data. Right.
Now, I do notice, though, that this pattern doesn't match every single peak.
It doesn't.
Is that a problem?
Well, if we
Does that mean this isn't the good one?
If we come back to the fingerprints on a glass analogy, it simply means that there are more fingerprints on the glass.
Ah, okay.
Right.
Okay,
so you can't identify
it
with one single fingerprint.
All right.
So one of the things that you can do is then you can apply what's called a residue.
Okay.
So a residue basically takes all the identified peaks and snips them out and says, you know what, I know what you are. I want you to search versus whatever you haven't identified yet.
Okay.
I've accounted for all of those fingerprints, digitally remove them from the glass, and then.
So we have to go in and kind of like cut them all each individually?
No, there's actually this awesome little thing called auto residue.
Oh, really?
I think the icon kind of looks like R2D2, but I've been watching.
It's a robot.
Oh yeah, it's a robot. It's a robot. Yeah, a generic robot that looks like a trash can. There is a trash can looking robot, but you'll see now my data here is in pink.
Yeah, so they're kind of like a salmon color.
Yeah. So this has been a generic pink fish. Yes. Yeah. Okay. So this has been cut out, right? All of these have been cut out. So then if I do the search match process again, what I'll find out is that now I've gone through and I've identified other ones, right? And you can again look for relative peak intensities. We see a little bit of shifting here that might be due to either some slightly subtle differences in composition. So if we see here, we see a bunch of different calcites here.
Yeah.
Magnesium substitution, not super uncommon. So you can either go with the first one, which has a slightly higher figure of merit, or you can go with one that visually looks a little bit better. But again, same process. Select it, add it to the pattern list. So I now have 2 patterns here. Residue it again, and then match again. So we've got this one remaining peak around here, 26.6. And what I should see, if my computer is going to do it. Okay, so right here, quartz.
Of course.
Of course, it's quartz, right?
It's quartz.
If you've ever been to a beach, you know sand gets everywhere, right?
That's right, sand on a beach.
Sand on a beach, right?
Okay.
So, all right, so I've done my phase identification. I've got 3 different phases. Looks pretty good. I'm going to close this, and then the last thing I generally like to do is this restore residual scan, just because it's going to bother me that this whole pattern isn't one color.
Yeah, it's kind of cut up here. Yeah.
So I'm going to restore it back to that, and then we're good to go. So
so what did we get? We got dolomite, calcite,
so dolomite,
and quartz.
calcite, and quartz.
So this seems pretty straightforward. I mean, there was a little bit of like you could choose some things, especially in that.
But if you went back and looked at it, you would see that 4 or 5 different calcites. There's like 8 different dolomites, and so that may be slightly different depending on the region where you got that route.
The local chemistry.
Right. Okay. And it's like these are naturally occurring, right? They're not necessarily synthetic. It wasn't necessarily a perfect single crystal. So there might be some variation there as well.
Okay. But you can there's also a tool I know called Automatch. And so it kind of does this, right?
Yeah.
So can we try it?
We can try it.
I'm giving Nate a challenge here. So if it doesn't work, this is all on me. Yeah. So we got like dolomite, calcite, and quartz. Let's see if we can get something close.
I'm a little bit of a skeptic, right? Because in terms of things like self-driving cars or like the self-parking ones, like I hate parallel parking.
Yeah, it's good, but you should guide it a little.
Yeah,
okay,
I generally do.
Let's see though.
So let's see what the Automatch looks like. We Automatch it. Let's see how.
So this is going to go in. It's going to find the best one, then it's going to cut it, then it's going to find the next one, cut it, find the next one, and then it's going to propose a list of things.
Yep. Okay. So it's proposing these 4 here. So dolomite, quartz, and calcite, right? This bottom one, you see that it's a very, very low figure of merit. So this is going to be kind of a question one if we look at the actual pattern itself.
Oh yeah. I mean, look at the bar. There's
it's all of these like tiny little like wiggly things. This is a data problem. This needs to be better quality data in order to do it.
And that's why the auto tool in the end, it's green. It's making those things green.
Yeah. These are proposed.
But it's not checking them. Right. It's saying strongly suggesting.
Exactly.
Right.
Yep.
Okay.
And so this, again, you can think about it kind of like match list, right?
Yeah.
It's a way to get you something that is less unwieldy to navigate.
That's right.
It's a smaller set of things.
And if you're going to use the auto tool, one of the big things, try to get a match list going. So you at least have a subset of the hundreds of thousands of possibilities. Right. So now, one thing I noticed is that all those patterns happen to have this number called I over IC in them.
Yeah.
And that means we can do some quant on it, right?
Do some quant
so I over IC, that's gonna be if they take the phase. Well, why don't you tell me what I over IC is?
Okay.
Well,
all right.
You're the expert.
Yeah. So I over IC is going to be used for quantification. So we've done the identification. Yeah. We've decided that with this particular rock, I would like to know how much dolomite do I have, right? Yep. How much quartz do I have, right? Yep. Maybe it's because carbonate rocks can be treated with acid or something like that. Maybe I want to get rid of those, but I want to keep the quartz behind. Yep. So trying to find out how much of each one is in there, you have this I over IC value. So if we look over on the right-hand side of the screen here. Yep. So like I said earlier, so you've got properties, and then there is this I over IC value. So I over IC dB. So that's the database. Okay. Right. So I over IC is going to be the intensity versus the intensity of corundum. Okay. Basically, what these databases will do is they will provide this internal scaling factor, right? So it's the intensity of the biggest peak versus the intensity of the biggest peak of corundum. So aluminum oxide. So if you were to mix a 50-50 mixture of corundum and dolomite, and this other phase, the I over IC tells you the scaling factor of the other phase. Right, exactly. Okay. So in this case, it gives you a frame of reference. Yeah. Right. Okay, so dolomite is 2.5. So for dolomite, it's 2.5. 2.5, which means that this big peak here at 31 degrees compared to the biggest peak of corundum, which is at 35, is 2.5 times bigger in a 50-50 mixture. Okay. And so the important thing to note here is that when we talk about semi-quant, it's going to be based on this relative scaling of that. It's not like Rietveld, right, where we're doing the whole fit. Peak intensity. Just peak intensity. It's based on peak intensities. So it's a good guide. Yeah. If you really want the exact number, though, you're going to go to Rietveld next, right? Yeah. But this is a good guide. This is a good way to start out, especially if you have well-ground powder. Yeah, and I mean, I think it's one of those things like, right tool, right job, right? Yeah. And this is the nice thing about so this is called the RIR methodology, so the reference intensity ratio. Okay. So reference versus corundum. Yep. And the easiest way for me to think about it is like if you wanted to give someone's weight in a non-standardized format, right? It's like, how many of these specific watermelons do you weigh? Sure. Right. Yep. You have to calibrate to one watermelon. Right. Yep. And so, like, same thing here. It's like, we have to calibrate to something, and that's universally been decided, 50-50 weight-by-weight mixture of corundum. Okay, so we all have the I over ICs. Yep. So now, what do we have to do to get the quant? Nothing. Nothing. So when you pull in patterns, if they're centered and they have the right and peak intensities, then they're going to be, so one of the things I'll do is I will show this with the proposed background. And you can actually see that the intensities are pretty close to where they need to be. There might be a little bit of, might be a little bit of adjustment that we can do here, but for the most part, we're pretty close to the max intensity. So right off the bat, I get a quantitative number. I get a quant here that says 60.5% dolomite. 11% quartz, and whatever the remainder is, doing math, 28.6% calcite. So that's a little bit like, I don't want to have to click through all those screens, Nate. Yeah. Is there a way that we can like make those numbers pop up in the little legend? Yeah, the easiest way to do it would simply be to modify our legend. And so one of the scripting options is, so say instead of the PDF card number, maybe what I want to do is show all these different options here. I want you to give me the compound name, but I also want you to give me the semi-quant. So that is, I think it is all the way at the top. A lot of choices. A lot of different choices there. I think it is SQ. Yeah. So curly bracket, SQ, curly bracket, and then if I click off to the side, you'll see that it is. Oh wow! That cleans it up right away. Yeah. Now what if? What if I want a pie chart? You wanted a pie chart? Can you do that? I could, but I don't like pie charts. I like bar charts. I like bar charts. Can you make a chart? You can make a, we can make a pie chart. So so everything is going to be right clicking, right? So if you right click over here on your 2 theta, our pattern list, that's what we're doing. So we want to make a view of the patterns. Okay. Right. So we're creating a view of the patterns, and we would create a chart view. So by default, this is a pie chart. Yeah. Okay, that was easy. I don't love pie charts. I prefer bar charts. So I'm going to what's a bar chart look like? It looks like a bar, John. I don't know. Yeah, but everybody's bars look different. Everybody's bars look different. Yeah. So this is generally how I like to see my data. Yeah, there we go. And it's all right there. It's basically it's basically histogram. Yeah. So here's my pattern. This is quantification on it, so you can very rapidly see which one. Okay. So now this was a phase ID. It's phase ID. Yeah. So now maybe let's look at what if we have
what if we have a 2D data set?
Okay.
What if I got it from a detector, like a 2D detector, and I want to analyze that? Can the software do that?
Okay, so that's an interesting thing. The 2D, the word 2D can mean a couple of things.
Yeah.
The thing that I find more interesting is actually a stacked 2D plot. So it is a 2D assemblage of 1D plots,
Yep.
right? So say, for example, so I've got some data that I had set aside, and it is going to, let's see, the material called theophylline. And what we did was, we hydrated this material.
Okay. So you had the material, and then you added water, humidity somehow, and
so
then
you
it
spritzed
changed.
it, or I'm originally from New Orleans, so you could just leave it out on the counter, and 30 minutes later,
Well, that looks very confusing.
So this is very confusing because it is a lot of stuff on top of each other.
Right. I can draw no conclusion by just looking at that by itself.
Well, yep, it's crystalline. Yes, there's something crystalline in here.
Yes, there is something crystalline.
So one of the things I like to do is called this waterfall display. So waterfall display basically cascades your scans, and you can manipulate this in both the X and the Y direction.
Okay.
And what this will allow you to do is generate these plots that are stacked on top of each other.
Oh yeah, now I can see that there's certain peaks that are appearing.
So if I adjust this a little bit so that you can see what's going on, you see that you've got peaks that are kind of going away, and definitely peaks that are coming in.
Yes.
Right. So this set of peaks down here, this is gone after say number 6 or 7 or something like that. Again, these come away 6 or 7. These peaks start to come in kind of rapidly, right?
Okay.
So just to give you a little bit of backstory about this scan, so I took this material, I spritzed it with water, and you can have a couple of things happen to a material. Either it could get wet, and it's just a wet sample, right? Or the water can start to change the structure. Yeah. The water can actually go inside of the crystal structure.
Okay.
And so that's what we're seeing here, is we're actually seeing a difference between crystal structure forms, one of them in anhydrous form, the other one is a hydrated form. So you are incorporating the water directly into the crystal structure.
Okay.
And so that's what we're seeing showing up here. So the waterfall plots I really, really like because I think it's a good way to sort of digest a lot of information very, very rapidly. Another thing that I like to do is called a 2D view. Okay. So important to make that distinction, but instead of a 2D frame of data, so like Debye rings, something like that, this is going to be a 2D map of peak intensity.
Of that data.
Of this data, right. So if I right click up here on 2 data, I can create what's called a 2D view. Okay. And what we end up getting is an intensity map.
Oh, wow. Yeah, now it's very clear, those peaks that are appearing and going away.
So yeah, so what this is this is going to be, so I'm actually going to switch to log projection. That's going to squish my intensities.
Okay.
White is going to be more intense. So we see white is more counts. Black down here is fewer counts.
Yes.
Right. And you can play around with some of the scale bars to see, like you can you're basically changing your contrast, right? So think about it like, an Instagram filter, something like that. You can change your color schemes over here. I happen to really, really like the blue one because I feel like you've got your gradations here, and then you have like the really, really white here that is going to indicate like the biggest intensity of your peaks, and then kind of fades away.
And if you happen to have collected this data on like a temperature stage or a battery cell where it's
humidity
connected,
stage, something like that,
humidity, you can actually even set the index, like the left side.
So you can actually, so in this case, my index, because this was just on a regular sample holder, is the order in which the scan was taken. But if you were dealing with a non-ambient stage, you could sort it by temperature. If you're going up and down in temperature, you can actually plot that as well. So you can see sort of reversible phase transitions. So in this case, we're simply just we planned our experiment, right? And so what we were looking to do is we were looking to see at what point do we see conversion? Right. So we start out with this phase here, and we end up with this phase here. So these 3 peaks right here. So maybe those are the three the card ones that you're looking for. And it's kind of cool to see how long do they persist. And we actually had this sort of intermediate region here where you see persistence of both materials. So it's not like you turn on a light switch and it's just boom, one material or another. It slowly starts to convert over it. Well, over the course of 1, 2, 3, 4, 5, 6. So 8 scans times 2 minutes. Okay. So over the course of 16 minutes, this converts over from one form to the other.
And by the way, while we're going through all of this, if anybody has any questions, we will get to those at the end of today's video. So go ahead and you can just type them in the right side of your YouTube window right now. Or if you have a question, later on, you can send it to our email address. That's live.events@bruker.com. That's right there at the bottom of the screen right now. So any questions, make sure to put them there. We will get to them. If you end up having to leave us, just because, you know, time, we might get a little bit longer today. You can see a lot of great info here. So you can always come back and watch the end, and we will answer your question that you had typed in. So let's get back. So,
with all of this,
yeah,
so one of the things that I thought was kind of cool about this particular one is looking at this sort of intermediate region, right, where you start to see these transitions. And so one of the more interesting capabilities of EVA that you mentioned earlier is this sort of like clustering, or this like selection over families.
So statistical analysis of data.
So basically, if we come back to the fingerprints on a glass analogy, right? If you have a bunch of fingerprints and you don't know who it is, but you don't really care who it is, you just want to know how many times that person touched the glass, right? That's what we're doing here. So we're looking at the patterns themselves without necessarily any information about crystallography or which phase it is or doing the identification. So I've imported all of this data, so I'm just going to go ahead and work with this data set. So we're going to right-click on 2 theta.
So you don't have to re-import it?
No. You don't have to re-import it. And I'm going to go to my tools, and I'm going to run cluster analysis. So this is going to give me options here. This is the you can apply some things for like checking for amorphous, or you can do like a background or something like that. But I'm just going to let it run at it. This data looks pretty good. And so what we see is that of this data, we see 2 pretty neatly separated families, right? And so if I look between these patterns, or if I say cluster 1, show me all of them, you can see that they're all kind of the same. And then if I look at cluster 2, and I toggle back and forth between cluster 1 and cluster 2, you can see, okay, I get it. I buy that those are different families of data. Right. So you can think about this dendrogram kind of as a family tree. Is that, at a certain point, everyone kind of starts to look like their parents.
So to be just clear, all of the little boxes kind of at the bottom of
each one of these is a scan.
Each one is a scan.
Each one of these is a scan.
And it's breaking it up based on how similar they are to each other.
So it's taking every pattern, every data point in every scan in this section. So it's honestly really, really cool that our software algorithms have gotten to the point where they can handle this number of computing problems at the same time, because I mean it's a lot of data.
And you can actually do hundreds. So where I found this very useful as a tool is when you start looking at HTS. Right, in the pharmaceutical industry, and people have gone well beyond the 96 well plate. Right now they go to 300 and some. And here you can just bring that data in, and then right there see, okay, these ones are related to each other. This is how they're related. And
we'll get back to that. I've got some cool stuff to show. I think on this one, right? So the one thing I do want to show here is this is so a 3D view. So 3D and then DS. So 3D. Metric multidimensional scalar view. And so this gives you sort of a 3-dimensional plot of what's actually going on. So you see that they're not really clean clusters.
What I can see is that there's that red group and the yellow group like before, but there are some that are actually closer to each other.
So if I select the 3 end members of this red group, those are, I mean, that's basically the same scan, right? If I select 2 that are kind of further apart, you start to see that there's some differences here, right? They're not quite the same scan.
And kind of expected in this data set where it's hydrating.
And you can look at, say, the 2 middle ones that are like very close to each other, and we've decided that this one looks more like red and this one looks more like the yellow family. But these 2 are probably more related to each other than they are to the clump in between. Right.
And this has nothing to do with databases and things like this. This is
we've
just
done no
similarity of a pattern to another.
Similarities of patterns only. And so this has been kind of cool to look at. And if we actually go in, and so what I did was I actually looked at the material both before and after. So I took a reference pattern. So if I wanted to look at the material pristine before, pristine after, I can go into this data set, and I'm going to go down to the bottom, and I'm going to add a reference file. So I'm going to add the references. I'm going to clear my data, pick the 2 reference ones. And so now I have reference patterns to compare each of the ones in the data set. Okay, so we're going to run that cluster analysis again. Run the cluster analysis. Okay, process. And you see that's pretty quick for dealing with this many scans
so it's
and
going
each data
through,
point.
Yeah, and you can do this on hundreds and hundreds. So,
And so here what we can do is, one of the options is the cell display view.
Okay.
And so if we look at each one of these patterns, you can actually see that every pattern is related to a reference pattern. So now that I provided it with those reference patterns, it can say for this first one, how much of this is of the anhydrous form, and then over here, this is all hydrated form. And here we see that it is a little bit of each one, right? And so we're seeing the red pattern kind of go away. The red. Here's your pie charts, right?
Yeah, there's my pie charts.
So as we continue to hydrate this material, the anhydrous form gets less, right? And then eventually it's gone. So I can say that this takes about 9 scans, or if these were 2 or 3 minute scans, probably about 20 minutes.
Yeah, and if you're looking at something like minerals or something like that, you could do a similar thing. You just have to bring in a perfect pattern of each of those components. And then it'll tell you the
And so one of the things I do want to show is, so like if I go in and I'm going to open up a new document, and I'm going to work with just a single pattern. So we said that, it was like the first 9 or so scans that we did. I want to actually add them in here on the set. So I'm going to add in a number 3 there. And then I'm going to add in the 2 reference patterns again. So I'm just going to look at a single pattern for expediency. So I've got my 2 reference patterns. I'm comparing this to one of my unknowns. And I can go through and do a quant. So this is not the same as the quant that we were doing before with peak sticks. This is now a whole pattern. So I'm not looking at the intensity of the peaks. I'm actually looking at the intensities of the entire pattern.
Oh, so it's actually fitting.
Yes. Yeah. And so each one of these shaded areas is going to be the reference pattern. So I've taken a reference pattern of the hydrate. I've taken a reference pattern of the anhydrous. But even if I didn't know that, I could simply just take a reference pattern of 2 materials that I expect to be in my unknown. And it's scaling them. Right? So it's going to scale them across the board. So even in these areas where you have like all of this really, really troublesome overlap.
Yeah, a lot of convolution.
You end up with sort of this whole pattern. Let's see if I wonder if I can.
And this will be a better thing because it's actually fitting all of the peaks, so it'll really.
Exactly. So let's see if I'm going to switch this over to square root view to kind of blow that up a little bit. Yeah. So you can see that this is quantification with the percentage of each pattern that is in the summation. So this is what we refer to as Squall. So it's semi-quant for all sample types. So whether they're crystalline, this works with amorphous materials as long as you can have a reference pattern of it. So this has been really, really handy for, if you're doing I over IC for, say, a glassy material. Good luck, right? How do you determine what your I over IC is? And so
I remember once there was some forestry groups out there, like government forestry groups. They don't, they're looking at wood,
cellulose,
right? They're looking at cellulose and wood, but they're really concerned about where does that wood come from? Does it come from a certain type of tree in a certain area? And depending on where you grow it, even though it's just a really broad peak, they do have signature patterns, right? So what they were looking at was actually just the broad humps. And they have a whole database of these broad humps that they use for determining.
A lot of fibers, any sort of synthetic.
Did this come from a rainforest versus did this come from the proper areas? So.
Well, so I mean, these are all the things that I wanted to show you. Should we get to some questions?
Yeah, but I'm gonna put a challenge. I might have to help
Nate
out here.
You want to see more?
There's the one thing I want to show just to make sure, and I know Nate's giving me this eye.
The look.
He doesn't like this. There is an example of 2D data in here. From a 2D detector, because I think this is an important feature too. So it's in the, so if you ever want, by the way, tutorial data, it's in a C drive of your install, and then it's under Program Data. And you go into Brooker AXS, and then you're going to go into EVA, or tutorials, and then into EVA. And in there's a 2D data set. So
which one do you want to look at?
I think if we just say core standard. Now this is going to bring in all of the frame files. Now this is from an older detector. This is from our Vantech. And this is data that's the debiring. So this is collected with a 2D. Now, if you have like an Eiger, a new one, it would actually get the whole thing, and it would be scanned and stuff like this. But you can see here how EVA actually brings in all that data. It's going to do any stitching that needs. So with the older detectors, you had to stitch. So it gives you that. And then you can click these cursors. So Nate chose here a wedge cursor. You can just graphically put it on there. And then you can actually integrate that cursor. So now what you do is you just integrate, and you can reduce that data down. And if you've collected a whole group of scans, you can actually, frames, say at different conditions, you can actually draw one cursor on the whole group, and it'll integrate each one. So this is something I think that really is game-changing in terms of the 2D work, because it really makes it easy to take that data, look at it, analyze it, and then integrate it down. And yeah, once you've kind of integrated it, like Nate is showing here, it's actually, you can stitch it all together, and now you can do the phase ID, do everything else you want with it. So if you have that 2D data, one software, you don't need to have a different software to integrate it. It's all here. You could even do, a lot of people like HTS, right? You're going to do snapshot views in 2D, bam, 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 bring it in, integrate it all, throw it in cluster analysis immediately, bam. You see in the well plate view, this is what's there.
Yep.
So your workflows really kind of change depending on what you're doing, but that's the thing about EVA. So you know what? One thing I learned though today, which is very important, is that we need another episode of EVA, I think, where we can dig even deeper into some of this stuff.
Sure.
Right? So in particular, you can even
Season 3.
Yeah, you can do some fitting and stuff like that.
Yeah.
Basic fitting. If you want to do really high-end fitting, Topaz.
Yeah, sure.
That's the place to go. But here you can do some great fitting. So let's get to some of these questions, though, that have come in. So let's see here. So first of all, we got from Ted, for waterfall and 2D plots, can you show the y-axis as temperature for high-low temperature XRD measurements?
Yeah. So if we go back to the screen, so the data that I was showing was not collected off of a temperature stage, so there was no associated metadata for that. But we do have a data set that has that. Okay, so this is going to be a lot of data.
That is a lot of scans.
That is a lot of data, right? So I'm going to create that 2D view. And if this is the data set that I think it is, one of the options you have along, so again, we see this intensity map,
the 2D view.
Log projection, right? One of the things that you can do is then, a little bit. I can physically feel the need to do my Windows updates. You can look at something called a side view. Well, one thing you could do is you could change the y-axis. So the y-axis could simply be, instead of index, you could do it as temperature.
Okay. And I noticed there's also one called tooltip, and then that's temperature too. So if you hover on one, then it'll actually pop out the temp too.
So this is going to be your y-axis. So now we have stacked from room temperature up to 220 degrees. Or if you wanted to do index here, which is the order in which the scan was taken, you could also do something called a side view. So the side view itself gives you this sort of like secondary view. The side view could be plotted with temperature along y as well. So you can have this one that shows you temperature along y, this one that then shows you index along y. So you end up with two combined views.
So yeah, there's all that metadata, especially if you plan these things in like a wizard. You can do the temperature, but now we also have the battery cells where the charge-discharge machine, what's the name of that thing? It's the
potentiostat.
The potentiostat. If you have a potentiostat, we actually have one now that integrates right in, so it'll write that metadata.
Yeah.
And
you can plot it versus like
right there.
Current voltage.
Yeah. Right. Yeah. And those are really, really cool plots.
So, good question.
All right, next one from AJ. It's, what is a reference pattern for 2D scan?
A reference pattern for 2D scans. Well, generally speaking, whenever people are looking at a reference pattern for anything, corundum's pretty common.
Yes.
Corundum, very, very common. All of our instruments come with a corundum standard, which is aluminum oxide. And so if you were looking at, say, trying to reference your detector or calibrate your detector position, say for the Eiger, right? The Eiger can be put at a very close location. It can dynamically go to a very far location. And you really basically need to determine how much 2 theta space am I covering depending on where I physically put the detector. And so we have a little corundum disk.
Yes.
So it's in this standard, usually. And then that will give you specific Debye ring positions and specific spacings between them depending on how close or far you are.
Yeah, so corundum, that's a great one. The silicon powder, you can get a lot of these from NIST.
Lab 6 is another one.
Yeah, and one thing that's really interesting about that corundum is that it's a sintered disk. And we always run it and then we look at the relative heights, but actually the heights are not perfect, right? They're not perfectly aligned.
They're actually textured.
Yeah, and if you run that in 2D, if you use a 2D detector and you scan it, you can actually see like this dotty line. It's not a perfectly uniform.
Well, I mean, if you think about
dividing.
any sort of ceramic that you've pressed and then heated, it makes sense, right? I mean, you think about like tiles, you think about like clay or something like that. So anything that you're going to put a lot of pressure on while you're providing temperature, which is growth of the crystals, the crystals grow in one direction. Right?
Yeah, and one other thing I would note there too is if you don't have a 2D detector, we actually also have this new method. It's called Bragg 2D. You can look it up on the web, Bragg and then 2D. And this is a way you can actually use a Bragg-Montano geometry with a line detector to generate some of these 2D graphs, and EVA supports that directly. So a great way to know if your sample's prepped correctly. Next question, how we can get it. Now, granted, this is kind of a follow-up to the reference pattern for 2D scans. So I think we answered that, but I'm going to take it a different way. How can we get this software? You had mentioned brookersupport.com.
Brookersupport.com.
And with EVA, you can always download the latest one.
Yep.
The way it works is that your license on your dongle, it might version lock certain features if we have new features.
You can always run our latest version of EVA.
Always run the latest, so you'll always have bug fixes, and sometimes we do put new features in there to everybody. So for the semi-quantification using EVA, what would be a better approach? Compare intensities of the most intensive peak, as you explained, or calculate the area using the peak fit option and compare areas.
Oh, we were getting into an entire episode of quantification, right?
Yeah.
So it all depends on how you want, which methodology you want to employ, right? It's like someone says like, oh, I want you to make dinner. Okay, what does that mean, right? Like do you want Thai food, right? Do you want Italian? Do you want do you want stir fry, right? Or, and then like in terms of the method, it's like, well, how do you want to do it? Do you want to bake it? Do you want to grill it? Do you want to saute it? Do you want to use a wok? Do you want to use an air fryer? Like, you're still technically making dinner, right? But quantification is
your
like that.
opinion. Let's just take this question at face value. In your opinion, compare the intensity of the most intensive peak, as you explained, or calculate the area. In your opinion, which one? It depends.
It does depend. It does depend, right? Because like so if you were doing, say, like peak fitting or something like that, peak fitting would account for area.
Yes.
And if time were no object, if teaching and education were no object, then areas are technically something that I would prefer, because one of the things that we don't really have time to get into, though, is crystallized size broadening.
Yes.
So as a material gets smaller and smaller crystals, so as you grind it more, if you're working with nanoparticles, your peaks actually get like shorter and wider.
Yes.
Right. And so the shorter, wider peaks take the same amount of intensity and they smear it out over a wider 2 theta range. And so this is one thing that if you were only looking at the top of the peak, that may propagate some error in terms of your intensity. So if you look in the if you look in any of the databases and you look at say a nanoparticle that's been added to the database versus like a very, very crystalline, large crystal particles, you might see different I over ICs, and that would be expected. So area would be one way of doing it, but area, then you need to start thinking about how do I handle like these types of like areas. So Squall may be one way of handling that with like RIRs. Maybe at that point you were looking at, say, whole pattern fitting with, say, either Squall or looking at Rietveld methodologies. Maybe you're looking, if it's a very simple control system, something like dequant, which is a calibration curve method, which can handle things like integrated areas rather than just the top of the peak. But,
I mean, I guess the way I've done it, and maybe you can say if it's completely off base, is if I look at the peaks, and they're kind of lining up with the patterns, it looks like it's a good powder pattern, and the peaks are about the same width. Then that means that you don't have this situation with a really soft material and a really hard one. If you got that, then when you grind it, you're going to have totally different peak widths, and that's going to screw up that RIR method, right? So what I generally do is I kind of look at the pattern and I say, you know what, the peaks are about, they look around similar shape, and the relative peak heights, they're kind of matching their patterns. I can kind of trust that RIR a little bit more.
But I mean, that's the thing. If you want to use RIR, and you want the speed and the convenience of using that methodology, you are using peak intensity, the top of the peak, and that's just, I mean, that's the end of the RIR part of it. It's like if you want to use RIR, you have to use peak intensity. If you like to use something like area, then you need to be looking at other other data handling.
Yep, and that is one feature. It will take way too long to go through it today, but you can actually use this.
Quantification is a 4-day class.
Yeah, you can use this fitting feature though in EVA with the patterns where you can actually fit, and it does take into account some of these things.
Yep.
But one thing, maybe really quick, I know we missed this, and I think it's important that we show this, is if you could just pull up a single scan maybe and show us how you have that area tool. That's actually a really, really valuable tool to be able to see. A very basic tool. So what the area tool is that you just bring in a scan and you say, I want to know where the peak is. I want to know the area of the peak. So I just want to do that basic statistic. So Nate just kind of like right-clicked. He said, create area. Pops up this box. And then right there,
I mean, you
got all the statistics.
You've got an estimate of crystallite size. You have integrated areas for top to bottom. So if I zoom in on it, you can actually see where if I append this, you can see it. Right.
Full width at half max. And it gives you several different quants for the actual peak position. So the actual peak of most intensity, the area,
weighted average,
the weighted average, all that.
Yeah, biggest thing.
That's a really nice feature too. So let's get to the next question here. With software like this, who needs scientists? I guess that's a comment.
I know, that is a comment. That's a mood.
You know?
Yeah. Well, and so
it's a good comment.
It is a good comment, right?
But you could see in there, actually, with the phase ID, there is still intrinsic knowledge.
Well, and I always like to think about it this way, in that, if you, like a more trained scientist, a more experienced scientist will always come to maybe more laborious work, right?
Yep.
But, any sort of specialist is going to have sort of these instinctive things, right? My background's in chemistry. And, when I started doing a lot more of geology, it was things that, I had been interested in as a hobby. I collected rocks as a kid, had like mineral specimens and whatnot. I'm like, oh, it's really cool looking. But in terms of understanding why these things were important in sort of an applied manner, right? That wasn't quite there, right? Experience builds more experience. And it provides, I think, context and color and shading, and okay, so these are different patterns. I know that, but like, why is it important? There are moments where which I think is fascinating about my line of work is that on any given week I could be working with anyone. I could be working with someone in pharmaceuticals. I could be working with someone who is making confectionaries. I could be working with someone who works in a crime lab. And one of my favorite moments is whenever someone is looking at a piece of data and they go, aha, right? The aha moment. And I'm always curious to find out, like, what is it about this piece of data and that piece of knowledge that you're tying back to something else? Are you tying it back to another method? Are you tying it back to, to NMR or IR? Or are you, is this it solves a problem that you didn't think about from a diffraction standpoint, but 3 steps further back along the process, you know why that happened. Right?
No, I mean, what brings to my mind is I remember going out to some sites with like these the drill guys or drill people, I should say, and stuff like that, and they're like, hey, you got this cool new XRD, and they're like, why do I need that? And you're like, because it will tell you exactly what's in the thing you're doing, and they're like, okay, you mean like in the rock or in that? They like grab a thing of it, they kind of run it in their hand, they might like smell it. Maybe even like if you get the ambitious one, they might even get a little taste. And then you're like, I can tell you right now, this is 43% this, and 15% that, and 16% that. And you're like, well, how about we just do the exercise? Let's just do it. I mean, and then sure enough, you run it, and they're like, But then you go, but by the way, did you know there was 2.5% of this?
Oh my gosh.
No, but that explains a lot. Right? So phase ID by eye. But you know what? Phase ID by eye, it requires somebody who's been doing it for 30 years.
Well, I mean, the other thing is, like, as a synthetic chemist, you still need scientists to make the material.
That is true, Nate. That is true. Okay, so from Dave now, can the software interpolate between 2 pure end members to obtain compositional information for solid solution materials?
Interpolate between them. Well, the interpolation is kind of what was happening in that waterfall. In the 2D plot, right? And so we didn't actually have every pixel of data. We had certain numbers of steps, right? And so it was able to sort of stitch between the 1D scans that we had. And so if you have a quantification for each one of those, then it's very easy to sort of like draw presumably a linear regression. I guess it depends on how that process works. But you could do some sort of fit between that. and plot along the way. Same thing for like, so dquant is our calibration curve software, which we definitely don't have time to get into today. But basically with these fittings, you can do like a linear fit, you could do a quadratic fit or something like that. And as long as you have your calibrated values, then you know what that fit curve is. And so anywhere along your process, you can interpolate between them, right? As long as you have your n members.
So. And say as a materials person, metals, what I think about when I hear this, though, solid solution, I think like...
oh, you're looking at D spaces, probably. Oh, yeah.
Zinc and copper.
Yeah.
And what happens is, right, as you change that composition, it's going to just change the lattice parameter.
You're thinking about Vagard.
And so, in this software, actually, what's kind of neat is you can actually tune the cell.
Yeah.
So you can bring in the unit cell and then you can adjust it.
Well, we saw this. We saw this with the calcium magnesium.
Yeah.
Right. Depending on the calcium magnesium ratios, the peaks were in slightly different locations.
Yeah.
And so what you can do is you can pick one of those patterns. You can do the tune cell, like you're saying, right? And you can adjust the unit cell and fit it to your particular sample of calcite, right?
Yep.
And then depending on where that peak is, if you know where the two end members are along that spectrum or along that distance gradation, right? You provide an estimate for.
So you would have to do a little bit of manual math there, like the Vagard's law. So assume a linear extrapolation.
100% here, 100% there, and then somewhere in between.
And there are different patterns, for example, for that with the solid solution mixtures. So you can use those as bases. So there is that, like I said, though, there is something called tuned cell. Once you do the phase ID. Then you go in there under the properties, you can tune the cell.
Well, I mean, the other thing is like if you know which particular pattern or which particular HKL you're looking at. If you know your tooth theta, you know your D spacing.
That's true.
So if this is the 100 reflection, you just adjust the 100 reflection, and then you're like, that's my A. Right. Easy.
How useful is the background tool? That's from Joseph. How useful is the background tool?
The background tool is interesting, right? So one of the things people will be able to use the background tool for is for modeling an amorphous background.
Yes.
So if you had, say, so if we're looking at crystalline versus amorphous, crystalline is very sharp peaks, amorphous is kind of that blob underneath it. And you can actually use your background to sort of fit that blob. And what that will allow you to do is to provide a calculation of integrated area for the amorphous region, the blob, right? Integrated area for everything that's sharp and crystalline on top of that. And then the ratio of those two will give you a calculation of how much of your material is crystalline and how much of your material is amorphous. And so the background tool can be used for that. Otherwise, I don't generally do too much with the background tool. It is nice whenever you're looking at sort of the peaks, is to make sure that they're on top of the background, so that you're sort of coming from the same starting point. But probably I use it most for amorphous calculations.
And as with any background tool, just make sure you're not overfitting the background. That's going to cause you issues.
Judicious use.
But that being said, like when you're doing phase ID, you definitely want the background on.
Well, and if you have a very, very large contribution to amorphous, say your sample's wet or it's embedded in a polymer, and you do a phase ID, phase ID is going to look for intensity from background. And if you have your background here and your amorphous is here, it's going to try to look for peaks in that region. So it is good practice to adjust the background to fit your amorphous region and then do your phase ID, because your search match will be based off of the peaks, not off of your amorphous signal.
And then like Nate had said, there's this really cool function called degree of crystallinity. If you want to calculate that, there's a really great tutorial file that's included with EVA that walks you right through that. And looks like our last question from Kodaswara. How to access the PDF4 plus 2022 file?
PDF4. So you can go to icdd.com.org. I can't remember.
ICDD.
Just Google ICDD or the International Center for Diffraction Data. They've got a great website. If you're looking for, so they have a searchable website where if you're looking for specific material, you can search for your material and it will tell you which of the associated products are there. If you're only doing phase identification, often the PDF2 database is going to be enough. If you're starting to push into, say, like more engineered materials or, say, like organics would be the PDF4 organics. If you're doing repo work, PDF4 is also very, very nice. But a variety of different products there. If you have any questions, the ICDD staff is super, super knowledgeable about that product and very helpful. So yeah, definitely check them out.
So yeah, so what you do is you go there, you get a license from the ICDD.
Yep.
Then they're going to send you the software. Could be a link, could be a physical. You're going to install their software on your computer. You install the database.
Yep.
Then in EVA, in the folder, like are the different programs that come with EVA, there's something called the database compiler.
Yep. It's actually integrated now into the software.
Oh, okay.
Yeah, so if you go to Tools, you can say Start DSRD Compiler.
Yep.
So this is the database compiler.
So you'll go there, and then in the drop-down, you're going to see that installed database.
Yep. And
then you choose it, and it's going to recompile the database. Now, what that does is it's just sorting it so it works better with EVA, so it'll be much faster.
Yeah.
And the thing is, though, it does require the license. And it does actively check that that license is still valid.
So generally speaking, it's going to be, for most users, it's a single computer installation.
That's right. Yep. So, so they have all the details about, how you, like what the licenses are and things like that. PDF4s, I think, are generally 1 year.
Yearly renewals. PDF2, I think, is currently a 5-year license, 5-year seat.
And the other thing to note about that difference, too, is a PDF4 contains what's called structures.
Right. So for things like readfelt.
Yeah, so if you're going to do that next thing, readfelt, this is another feature. Man, we got a lot of features to talk about in another episode. Is you can actually, once you do the phase ID, you can save it out as an input file, bring the file into Topaz, and it'll already set all of your instrument settings, the phases are there already with the structure files, and then you can just fit. Yeah. So it really, really makes that easy.
And that really nice transition from like one software to the other.
Right. Yeah. That's right. So that is the last question for today. A lot of great questions. So thanks to everybody for joining. And thank you, Nate, for this great demo. We're definitely going to have you on again.
Yeah.
Because
happy to be here.
Yeah, this is great. And until next time, though, everybody, make sure you keep your signal high and your background low.
See you.